The Shovel Load Assist Program, or SLAP, is developing technologies intended to help operators use electric mining shovels. The Australian Coal Association Research Program, CRCMining, and Joy Global Surface Mining have joined together to invest in and develop this program. The aims are to improve safety, reliability, maintenance, and productivity. Currently, the operation of these complex machines is manual, and overextended use can lead to unintentional collisions. Risks include the shovel striking its own tracks, collisions between the dipper and other equipment, especially manned vehicles like dozers or trucks. These collisions are particularly dangerous given the presence of people. An uneven distribution of the load within the tray can lead to unsafe truck operation, maintenance issues, and uneven tyre wear. SLAP addresses these risks by providing a layer of automated protection to the operator. Testing of the new technology has been conducted using industry-standard equipment located at Brisbane City Council's Bracalba Quarry. The first outcome of SLAP is Track Shield. This system prevents the bucket of the shovel colliding with the tracks. Track Shield has a model that allows it to predict how the shovel will move under operator command. If this model predicts that the bucket will collide with the tracks, Track Shield calculates a change to the operator's commanded motion to steer the dipper around the tracks. The benefit of Track Shield is extended life of the shovel, and in particular the crawler tracks, improving the overall availability and productivity of the machine. The second SLAP technology is Truck Shield, which extends the concept of Track Shield by preventing the shovel from colliding with vehicles around it during the loading process. This system addresses some important risks. One risk is collisions between the bucket and the truck. When the operator is loading a truck, Truck Shield predicts collisions and alters the operator's command to steer around it. If the operator were to momentarily lose concentration, Truck Shield continues to act to avoid collisions. Here Truck Shield is raising the bucket over the tray of a reversing truck. Another risk addressed by Truck Shield is to stop the operator from inadvertently positioning the bucket over the headboard of the truck. This is a safety concern. The truck driver could be seriously injured if the payload were released on the headboard. A third risk addressed is to prevent the shovel house swinging into the truck. The third SLAP technology is Dozer Shield. Bulldozers come close to shovels to ensure the bench is level. In double-sided loading, the operator must keep track of the dozers in addition to the truck. Dozer Shield is conceptually similar to Truck Shield and prevents collisions between the dozer and the shovel. The fourth SLAP technology is Auto Load, which leverages the predictive models used in Truck Shield to provide an automated swing-to-dump functionality for the operator. When instructed by the operator, Auto Load calculates an optimal trajectory to manoeuvre the bucket into a waiting truck tray without colliding. It dumps material to the truck tray and then returns to the dig face. At any point in the cycle, the operator can retake control with the joysticks. This system improves the productivity of the process in several ways. It is more efficient than manual operation, as the computer can command the machine at its maximum speed and anticipate when to decelerate to be in the optimal loading position over the tray. It is more accurate and consistent in the even distribution of the load, which improves truck safety and maintenance. Additionally, Auto Load reduces the operator's mental workload during loading, allowing them to concentrate on developing their dig face more productively. Risk-based development, a case study. One of the key pieces of information required by the Truck Shield and Auto Load technologies is the location of the truck in relation to the shovel. In the development of these technologies, the engineers set out to find the most appropriate way to solve this problem. They considered 60 different approaches, but found there was no single approach that worked flawlessly. All the methods had ways of failing that meant that they couldn't be used alone. 3 approaches were chosen that didn't share the same flaws, giving a redundant solution that has high integrity. The first approach generates a model of the terrain by scanning it with lasers. A spinning sensor constantly sends out beams of laser light to hit the surrounds. By measuring the time it takes for the light to return, the distance to objects in the world can be measured. By making a large number of measurements, the location of the truck can be established. The second approach uses pulsed radio to find the distance between transceivers mounted on the shovel and truck. From these, it can work out the location of the truck relative to the shovel. The third system uses high-precision GPS to find the location of the truck. These 3 solution methods feed into a computer model. When at least 2 out of the 3 agree, the position of the truck relative to the shovel is taken as known. Finding truck location is an example of one of many safety functions implemented in SLAP and allows for safe and reliable support of operators. These technologies support operators of mining shovels. The developments move us further along the path of creating a semi-automated mining shovel. Repetitive tasks can be performed with uniform reliability, raising productivity, lowering costs, and removing the risk of injury to make the mining industry safer and more profitable. The development of SLAP technologies has benefited from the financial support and vision of the Australian Coal Association Research Program.